So let's move on to our next and the last speaker of the conference.
Before the panel.
Before the panel, which everybody needs to be here. So, Yordanis Karanidis, our next speaker, director of QCware France, director of Paris Center for Quantum Computing, director of research at IRIV. He's doing a lot of directorship, and yet he's the expert in research in quantum machine learning and quantum algorithm, particularly recommendation system and classification and clustering. So it's great to have you with us. He's famous, but also working with famous people. He was a postdoc of Peter Shor and PhD student of Umesh Wazirani. It's great to have you here. Tell us about the way that at QCware you're helping to bridge the ecosystem between end user and the algorithm.
Thanks a lot, Elham. Thanks, Olivier. I hope you can hear me.
Yes.
Excellent. I will be discussing about, kind of the holy grail of quantum computing, which is how to find useful applications, right? And let's see how we can try to do that. So we talked a lot about how the hardware manufacturers are trying to make better hardware, right? And this is very important. We need more qubits, we need better qubits. Otherwise, we won't be able to reach these quantum applications. But what we try to do on our side is figure out ways to take these quantum algorithms that exist or that we design ourselves and figure out how we can take their impact and be able to do it with machines that can have less resources, like fewer number of qubits or less quality qubits, and still have a very good performance, right? So we're QCware. QCware started in 2014 in Palo Alto in the Silicon Valley, and we created QCware France in Paris in 2019. We're extremely happy to be in Paris because there is a very big ecosystem which is getting started, and we're very happy to be part of it. These are only some of the players within Paris that we are discussing with and collaborating. And what we do is we focus on computing problems, right? So the main question here is that what are the difficult computational problems that we have issues resolving them with current classical computers? So this can have to do with chemistry simulation or optimization, Monte Carlo methods or machine learning. I'm really sorry, I have to stop for 1 second.
I told you, he's director, so he's a very busy person. He's getting phone call. He needs to answer all of these things, but he'll be back with us.
But my Alexa decided to start talking by herself, so I'm really sorry for that. This is what happens on live talks. So these are kind of the main problems that we are trying to understand what quantum computers can do, right? And we're designing quantum algorithms. This is what I have been doing for more than 20 years now. And the whole team at QCware are experts on quantum algorithms. And today we'll be discussing more about machine learning, right, which is kind of my specialty. So let's go to quantum machine learning. So why do we think that quantum machine learning is a good area where we can find quantum applications? Well, the first question is that the first reason is because we know that if we had fault-tolerant, big-scale quantum computers, then we can offer big advantages, right? There are many different algorithms that have been developed for quantum machine learning. These are some of our results on classification, recommendation systems, clustering, and all these things. So the question after that is, do we have to wait for these big-scale universal quantum computers, or can we start doing something and experimenting even with the NISQ machines, right? So what we think is that we do have concrete ways and concrete avenues for bringing this quantum machine learning closer to reality. I'm not claiming that today or tomorrow, we will be having industrial-level machine learning applications with the existing quantum computers, but what we're trying to do is reach that point as soon as possible, right? And for that, we had to develop many basic tools, basic quantum tools. The first one has to do with data loaders. How do we take classical data and load it into the quantum machines in order for the quantum computer to run the algorithm and do something interesting, right? How do we estimate distances between data points? This is kind of a fundamental primitive for machine learning, and especially for similarity learning. And how to do more generally linear algebra, which is kind of the core of machine learning. And one more thing that I wanted to say is that there are many different things that one would need from machine learning and also from quantum machine learning. Of course, we're talking about efficiency and accuracy, but there are also other very important things like interpretability, trust, energy saving. And quantum computer can also help offering such properties. So what I want to do from now on is just look at one particular use case and go through all the steps that we need to do in order to show that quantum computers eventually will be able to provide some impact in this use case. So here is the use case that I decided to discuss. We're talking about medical image classifications, right? We have all these different images, and we need to come up with a machine learning algorithm that can, for example, see if there is a problem with some patient or some MRI, so that we can do more exams, or we can order some medicine, or there is no problem, so everything is okay. So how do we classify medical images, right? So the first thing we have to do is figure out what is the algorithm that we should be using, right? There are many different ways of classifying, classical ways. You can talk about similarity learning, like nearest centroids or nearest neighbors. We can start talking about neural networks, like convolutional neural networks, autoencoders, Boltzmann machines, support vector machines, which is also a very interesting and more interpretable way of classifying. So the first question is, which ones of these methods can be done quantumly, and whether quantum can offer something on top of these classical methods, right? So what we did is that we chose to work with the nearest centroid. There are quite a few reasons why we decided to do that. The first one is that basically it's the most fundamental way of trying to classify. It's the easiest way. If we didn't know how to do anything quantumly on that case, maybe it wouldn't be possible to do anything at all, right? It's also a very clean way to test our quantum machine learning subroutines, right? On how we load data, how we do distance estimations. It's a very clean way of testing our quantum subroutines. And it's also a very interesting way of benchmarking the hardware. We talked a lot during the day about how do we benchmark the hardware. On our side, the best way to benchmark the hardware is by understanding what applications they can solve, right? So let's see what is the nearest centroid classifier. It's pretty simple. Imagine you have three different classes of data, the blue ones, the green ones, and the red ones, right? And what happens is that a new point, which is this white point in the middle, comes, and we don't know if it is blue, green, or red, and we need to assign a color, right? So the first part of the algorithm is what we call the fitting the model, and what we do is that we look at all the blue points and compute the average blue point. We look at all the green points and compute the average green point, and the same for the red ones. So we only keep these 3 points, which we call the centroids, right? And when the white point comes into the picture, then we just compute the distances to these 3 centroids, find the ones which is nearest to us, and then assign the corresponding label. So for example, at this example, the white point should become green because it's closest to the green centroid. So what is the simplest way of trying to do a quantum analog of this algorithm? Well, instead of computing the distances to the centroids classically, we can try to compute them quantumly. Of course, this is not the only quantum step that we can do in the algorithm. We can devise even more quantum versions, right? For example, we can also start estimating the distance to the centroids in superposition. Altogether, we're using this parallelism of quantum computing instead of one by one. But we're trying to see what is the simplest quantum thing that we can do, and we can try to start implementing it even with the machines that we have today. So before we are able to compute these distances quantumly, we have to load this classical data into the quantum computers. So how do we do that? Well, we don't need QRAM or any kind of weird things that we discussed a bit during the day. What we need is some simple circuits that we can use that have parameterized gates. What we do is that we look at our classical data, we define the parameters of the gates of our quantum circuit, and then whenever we want to create a quantum copy or a quantum state that corresponds to our classical data, we just run this quantum circuit. What is the very good thing about this quantum circuit? It only has logarithmic depth, meaning that in log time, one should be able to create a quantum state that corresponds to this classical data. And this is exactly what we want in order to get all the advantage possible from the quantum machine learning algorithm. Here is a little bit more how the data loaders work. I don't want to get into the details. The one I defined before is this parallel data loader where we use n qubits and log n depth. We can trade off the number of qubits at the depth. This is kind of goes back to the discussion that we had during the previous session. Do we want more qubits or better qubits? Well, depending on what you give me, I can trade off between these two resources to get the best I can out of the machine that the hardware manufacturers make available. Once we know how to load our points, then the next question is, how do I estimate the distance? I don't want to go into the details, but we can also construct these very, very shallow quantum circuits that use these ways of loading the classical data in order to create a circuit that can estimate the distance of these data points, x and y. Okay? We know how to do that now. So now we are ready to develop the software. So our point is to develop a software that is able to be used by classical data scientists, right? We want everyone who knows how to use classical machine learning to be able to also start using quantum machine learning. And for that, we are using very simple software techniques. I show you here how to generate some classical data. I show you how to use this function that we have, which is a fit and predict function for the Q nearest centroid. And in order to see that it's extremely similar to what a classical machine learning person would do, I just also put here what scikit-learn does when one wants to use the nearest centroid algorithm. Again, you fit your data and then you predict, right? Let's print the labels. This is the outcome of the quantum and the classical algorithm. You can see that they are the same. I can even plot them. And you can see that the way that the quantum algorithm classifies this synthetic data for now is actually the same as the classical one, meaning that it can do very good classification. This is the software that for now it's simulated, but we went one step further, which I will show you once I show you what do I mean by developing the software. Many times people think that developing the software is just an aftermath and it's very simple, but this is not necessarily the case. There is a lot of software that has to go into the background in order to be able to have some classical trained person be able to go all the way to the quantum hardware. We had almost 1,000 lines of code to do that. And this is something that we do through the project of the INNOV concours from the BPI France. And once we have the software, we are now ready to execute it on hardware, right? So we got together with one of our hardware partners, in this case, IonQ, because they have very good qubits. We performed some specific hardware combinations now to be able to use specifically their hardware. We found the right data sets, and we were able to benchmark our results. And here is what we got. For 4-dimensional data, we get accuracy 100%, not bad. For 8-dimensional data, we get accuracy more than 98%, which is also very, very good, right? And these are results that actually come from executing the algorithms on the quantum hardware, not by simulations or emulations. We also used some data sets that people use in order to kind of benchmark their machine learning models. We use them in this data set. And here we got also results very close to the classical ones, not exactly as good as the classical ones, but much better than what we expected. And of course, this is something that we have to continue working on because, we are going against classical machine learning algorithms that they have been developing for decades now. And we are just starting to understand how quantum machine learning actually works.
Yordanis, can you wrap up in 2 minutes so we have some time for question, please?
This is perfect. Yes. I also wanted to say that for us, this is also a very good way of benchmarking the hardware. So we can ask a very simple question for whatever hardware is out there, what accuracy and what efficiency can you get for classifying 8-dimensional data, for example, right? You can work on the algorithms, but also you can work on the hardware, and let's see how we can find what are really the parameters of the hardware that we care about for such applications. Do we care more about the number of qubits? Do you care more about the quality of qubits and so forth? This is only one of the applications. We can use similar techniques to start talking about quantum neural networks, about regression techniques, clustering. I'm not going to talk about all this. I just want to say that there are two very, very important things that make all this possible. The first one is that we have to work very closely with the people that have actual problems. So we want to solve use cases that come from people that have actual use cases, right? And this is some of our partners. We also want to be able to run our circuits in any hardware we want, and also we have connection with all these hardware providers. And to finalize, because Olivier asked before, what is your business plan? So for now, we are providing services. We're having a 2-day workshop and proof of concept projects that we have so far done more than 30 with industry partners. And we also have a product which is a software cloud platform that sits on top of the hardware. It's hardware agnostic, and it also sits on top of cloud providers like AWS and Azure. So our main goal is to make the most performant application software out there. So to conclude my last slide, I want to just reiterate that new algorithms make the biggest computational leaps. We always think of hardware as making leaps, but actually the biggest computational leaps happen from new ideas on algorithms. And actually what I wanted also to say is that the competitive advantage also comes from algorithms and IP. We will all have access to the same quantum computers. Whether they are good or better, we will all get access to them. The question is, what are we going to be running on them? This is exactly what we should be working on, which is quantum algorithms. And I finish with the last question. It's just a small provocative question. We ask our partners, if you could go back 5 to 10 years, what do you have done differently with respect to AI, right? And here is what they say. We would have invested earlier in getting internal knowledge, and we have started thinking immediately how to incorporate machine learning in the workflow. So we are at this point in quantum technologies. So in the question, when do we need to start getting involved? I think the right answer is right now. So thank you very much.
Great. Thanks a lot, Jordanis, to walk us through this very concrete use case. While we're waiting for more questions that is showing up in the chat, maybe I ask something just in order to conclude. What is the path? I mean, you already alluded to for the quantum software productization, which I think some term that Olivier invented. Are we at the stage that we can see this concrete quantum algorithm as a product that we can sell? I mean, this is the model you see, or you're still seeing that it's going to be in this ecosystem of services and linking the end user. So just want to know your view.
Yeah, this is a very good question. So on our side, QCware is a quantum software company. Right? This is our goal. Right now, it is not easy for people to start using quantum software, right? And so right now, most of our revenue comes from services, but through the services, we are using quantum software, and we are developing expertise within our clients on how to use quantum software, right? So we're designing the algorithms together. We are building the software together. They get to understand how the software is used. And I do think that in a few years, when the hardware will get also better, more and more people will want to start using quantum software.
I have one question also in the chat from one of your former students, so I'll let you guess who was it. So is an efficient version quantum data loader circuit proposed for binary encoding? With unary encoding, even though the circuit depth is logarithmic in the size of data, you need a lot of qubit to start with. Also, it is easy to see how to map the classical data efficiently into parameterized circuits if one is using binary encoding. So,
yeah. So, okay, it's a bit technical question. I guess it does come from one of my students. So there is a limit on what you can do. There is no free lunch, right? So no matter what you do, you need a circuit of size n if you have n variables to encode, right? And what we can do is play with the number of qubits and the depth. You can have n qubits and log n depth. You can have square root n qubits and square root n depth. You can have whatever you need. On the other hand, you could have log n qubits, but then you would have n depth, right? We do think that it's easier to get more qubits and less depth of lesser quality. This is what physical qubits look like right now. And this is why we're using the parallel ones. But there is no way to load things without having enough parameters that correspond to the classical input.
Okay.
I hope this is clear.
Excellent. So looking forward to the day that quantum machine learning can improve the performance of Alexa, not to interrupt our online talk. With that, I'll thank you very much for joining. And we are going to prepare for the last panel about the French ecosystem. Thank you very much, Jordanis.